All right, let's talk about another type of projectile motion here. So this is horizontally launched projectiles. And we started this off with a little experimentation and a little bit of a vote on whether we thought that if we were to launch an object out this way and drop an identical object at the same time, we wanted to know which one would hit the ground first. Okay, so from the same height, if one's launched out and one's dropped, and we found that both would hit the ground at the same time, okay, which is sometimes a little bit counterintuitive for people. Oftentimes people will think, well, this one has a farther distance to go, it must take longer, okay? But what they're sort of forgetting is that there's two planes to consider. So we've got our y plane. Well, in our y plane, you have an acceleration, okay? And when these things start off, their velocity in the y plane would be zero, regardless, right? Assuming this is launched perfectly horizontally and this is dropped, their velocity in the y plane is zero, right? In the x plane, okay, well, this has no x plane velocity whatsoever, but this does, okay? The x plane velocity acts completely different. There's no acceleration in the x plane, okay? You might say in reality there's probably a little bit of air resistance, but over short distances, this is kind of pretty much negligible, okay? Or we can say this is happening in a vacuum. You will find that both these hit the ground together. This, I won't say it's a problem, but this issue was dealt with by Galileo in a pretty famous thought experiment. So I'm just going to reiterate what that was. So he said, imagine, this is Galileo, and he helped us to understand why this has to be true. Okay, and he said, imagine that you've got a boat in a river, and that boat is traveling along at some velocity, and let's say that you have a person up in the crow's nest on top of the boat, and they drop a cannonball. Okay, now think about their perspective. From their perspective, the cannonball will accelerate down and it will land right below them on the deck of the ship. Okay, you can see the same effect when you're driving along in your car and you're sitting in the seat and you drop something. Well, it does not come shooting back and blast you in the face. It drops straight down below where you let it go, right? You and the car are in the same plane of motion, okay? Now, what is a person on the shore, right? Sea. They're looking out to sea. Here's the shore. Well, in the time that this falls, this boat may have moved over to here. Okay, this boat has traveled along. And so what they're going to see is they're going to see this ball at the same y height that the other guy does, but it has also to it now, from their perspective, an x velocity. From this guy's perspective, there is no x velocity, right? He's moving along at the same speed the ball is, so to him it falls straight down. To you, though, on the shore, or to someone on the shore, it follows this path, right? This sort of curved path like this. Is this a different ball in each scenario? No, it's the same ball. The time this guy senses is equal to the time this guy senses. The reason being is because it's the same guy. And this guy senses the same time as both, right? And so we're seeing the same action in two different ways. So this is back to relativity, all right? So just because this travels a farther distance, okay, does not mean that it's a different ball. The same ball can travel two different distances depending on who's looking at it, all right? This was kind of a big deal, right? And what it sort of showed is there's an independence, if you want, between x and y plane motion of objects. And it also kind of leads into the whole idea of relativity, but we'll sort of leave that for later. So the main takeaway that we need to get from this is that the time to the ground for a horizontally launched object is the same as that of an object dropped from the same height. And that is even true for, like, you know, a bullet shot from a gun, right? And a bullet dropped at the same time. Both will hit the ground at exactly the same time, okay? Even though this one moves, you know, way far away while it's doing that, it still has the same acceleration in the y-plane as a dropped bullet. So we can do all kinds of problems with this. Let's try one of the most standard types that you would get. Let's say you have a 10-meter high cliff, and let's say a ball is launched at a velocity of, I don't know, let's go 15 meters per second, okay? So it's going to travel away from the cliff. It's going to come to rest 10 meters below where it started. Now we might want to say, what is the range? In other words, how far away from the cliff edge did this land, right? Now we have to understand that we know that this will take the same amount of time to get to the ground as if we just dropped it. So what we need to know is time to the ground, right? And that's going to be the same no matter what this number is. This number could be 1,000, and it would be the same thing. I have to be a little careful because there are some effects caused by air. Like, for instance, if the bullet's rifled, like if it's spinning, then there can be some changes to how it travels. So we're going to kind of, I guess, say the air resistance is negligible, or say it's happening in a vacuum, so we don't have to actually acknowledge those problems like you would get with a rifled bullet. So we'll just leave it as kind of this for now. So time to the ground. How do I solve for time to the ground? Well, I've got d equals 10 meters, right? I've got g equals negative 9.8 meters per second squared, right? Now I need to find time to the ground, right? And so one more thing that we should acknowledge, okay, is that we have to kind of look at the two separate planes of motion, and that VIY, the initial velocity in the y direction, equals 0, right? So maybe that's one more thing to put in here. VIY equals 0, okay? So, anyone? So we got to go back to our kinematics formulas and realize, okay, just ignore the x motion now and just talk about the y, that this moves the same as anything falling 10 meters, right? Or time-wise, anyway, it falls for the same amount of time as anything falling 10 meters. So we're going to go back to, this is VIY t plus 1/2 at squared. We know that VIY is 0. So we rearrange this to d. So we get t equals root of 2d over a. So in this case, 2 times negative 10 meters, it's going down, so negative 10 meters, divided by negative 9.8 meters per second squared. We should get, so it should work out to be 1.42 seconds. Okay, so what that means is this object is in the air for 1.42 seconds. 1.42 seconds. Now, during that 1.42 seconds, it is traveling at 50 meters per second in the horizontal. So now we look at that separately. The range will be the same range as anything else traveling to the right at 50 meters per second for 1.42 seconds, right? So it'll get as far away here as it can. And when you think about it, what's going on here is it's knocking off time in equal amounts in this direction, right? And it's knocking off distances in increasing values over here. So we sort of like match these up. The result is you get this parabolic or curved sort of path. You kind of line up where it is in each plane. So the final answer to find range, now it's just your standard displacement in the x equals my velocity in the x times the time I'm doing it for. So 15 meters per second times 1.42 seconds. We should get 21.4 meters. I don't know why this won't write right now, but 21.4 meters there. Okay? That's how far it goes. So just to remind ourselves why this follows a parabolic path, okay? So we launch it in this direction. Okay, it starts with a y velocity of 0. Okay, it will clip along through the air, covering, since its velocity is set in the air, right? It's a non-changing velocity. In the x direction, it always covers the same amount in the x direction every time, right? But in the y direction, it covers a little bit more each time, right? A larger and larger distance in the y every time because it's accelerating in there, right? So then you end up with this kind of, curved path that we're sort of used to from a falling object. And that really is all there is to say about that.